like edge. I can't.
Oh.
It sucks. Every time I just like.
Yeah.
I just so weird though, because that's the second time today we've heard.
All right, happy Wednesday, Monday.
On Saturdays. That's so.
You guys know what I'm in there?
Oh, yeah.
Yeah?
Yeah. I know. It's just yesterday. I don't know.
On
It's
over the
Monday.
weekend?
It was the shortest weekend ever.
Was it a short weekend?
We both went to Bogus, so we didn't see each other.
It's all right. Well, it's a pretty big mountain.
Yeah, that's what I'm saying. Yeah, I know the backside.
Oh, yeah, I was just like.
Yeah, I wouldn't.
I know.
I don't even know what my son's clothes look like. I rarely see him on that. And that's frontage, and that's small.
Yeah.
Yeah, kind of funny. Cool. Very good. Awesome. Yeah. Good. Ish. 2, 4, 6, 8, 10, 12, 13. So. Okay, well, we're going to finish up this chapter today. Anything you want me to clarify or go over before we jump in and finish this with Suzuki coupling? No?
We have an exam on Friday, correct?
Don't need them on Friday.
And then the homework for this week is a due Sunday as well?
It's going to be due Sunday night. Yeah, I want you to study for the exam and then.
Was there a homework due yesterday?
No, I haven't put the homework from last chapter or this chapter on yet. Okay, so organometallic is again the aha of this chapter. We should be thinking towards synthesis in the formation of carbon-carbon bond. That's kind of the big aha, if you will. We left off with a very important reaction we'll see on Wednesday. We'll work with it quite a bit, if not a little bit today. But we left off talking about the alkyne. We went through the pKa, knowing that the pKa of that proton is around 25. Okay? That tells me that a strong base is required to remove that, and that's so why we use sodium amide. Okay? Sodium amide is strong enough to remove that. So the first step in this reaction was to take off that proton and make the salt. Okay. And we knew that the reaction is going to go this direction because the pKa of our ammonia was 38. Okay, so it tells me that I'm going to force the reaction to go to the right. Once I have this, I hit it with some form of an alkyl halide, and then I can make a carbon-carbon bond off that and sodium bromide. Okay. This reaction has a caveat. And here it is. If I take this reaction, thinking I'm going to be all cool and synthetically minded, and I react it with an alkyl halide, and lo and behold, what I get out is this. What in the world just happened? Because that's not at all what I wanted to happen. What happened, Clayton? How come I didn't get this? Why not this? Because doesn't it make sense that if this pair of electrons attacks here, it kicks that off, that I form that new bond? So why not that?
Did it take an electron from the alkyne instead of?
No, what did it do? How many carbons do I have here?
3? Yeah.
What competes with substitution reactions? So instead of it substituting, it grabbed a proton and eliminated. Because remember, elimination competes with substitution. So the caveat of this reaction is typically we have to do it with primary alkyl halides. So this has to be a primary alkyl halide, or I'm going to force elimination on this. Because remember, this is a really strong base. It's a really strong base. And a strong base that sees a bulky substitution and say, too bulky to get in on that carbon, I'm just gonna go ahead and grab the proton and eliminate. And that's what happens. So you don't get any of the substitution, you get all elimination. All right, so that doesn't do you any good. So the one caveat of the alkyne reaction is that it has to be with primary alkyl. And that's not bad, because most of the time what we're gonna do with this thing is we're going to take, here's kind of the way I think of these reactions. You do have to do it in 4 steps if you're going to build this thing up. But if I start with acetylene, which we will on Wednesday, and it's okay to do this, sodium amide, because I know ethyl bromide, sodium amide, ethyl bromide. Okay? You can't just do 2 equivalents and 2 equivalents. It does not work. So in order to make this compound, in order to react it both on one side and the other side, I have to do it in 2 steps. So I have to hit sodium amide, take the proton off, have it eliminate. I have to take the proton off, have it eliminate. So I put that on both ends. Okay? And that's just, again, those are a couple of the little nuances of the acetylene reaction that we see. What's really nice about that is I still have my handle, and we'll see if we can work with that and begin to rearrange and do some fun things, some fun chemistry with that, okay? Now, that brings us to our final 2 reactions, carbon-carbon coupling reactions with metals. So this is kind of a newer area of organic chemistry. If I take something like copper, okay, copper being copper 1 or copper 2, depending on which one, in this case it would be copper 3, I can take this copper compound, and if you'll notice, this copper compound will basically help me react whatever it is I want to react. So this is going to be an R, and typically those R's are the same. And if I take this copper, again, organometallic compound, and I hit it with an R primed, something like an iodine or bromine, okay? What happens to this molecule is it goes to a tetravalent. So it goes R, R, R prime, I. Okay. So what's happening with this? I'm working on the overall molecule's ability to form these bonds in multiple ligands, if you will. Those of you that you just had inorganic. Do you have inorganic chemistry last? No one's had inorganic. Okay. So these are ligands. This is the type of research that Dr. Harris does. But you have multiple valence sites on these bigger metals. We'll see palladium with the Suzuki coupling here in a second. So then what happens is typically these two get together, and that's where your new carbon bond is formed. So you form that. Okay, so it's a carbon coupling reaction. So what you've coupled is you've coupled the R from the copper, and you're going to have a counter. These typically are these big organosalts. So you have a lithium plus, and these are all complexed with lithium. Lithium's out here floating around on these lithium copper compounds. Okay, again organometallic. what am I looking for? Ultimately, what I'm looking for is whatever R group was on my copper and whatever R group was on my halide, it's going to be the coupling of those two R groups. That's the power of these copper coupling reactions. Okay. One of the drawbacks for these is your R group here has to be either aromatic or alkenal, alkenal. Okay, aryl or alkenal. That's one of the drawbacks of that.
Question, what does
Yeah.
the R prime mean?
It just means this R is distinct from this R,
Oh, okay, that's, okay.
right? This could be, so for example, this could be
Mhm.
propane, and I could react this with like a benzene, like this.
Mhm.
So my product in coupling is going to be that.
So is benzene aromatic?
Yeah.
But is it also alkeno? Cause it.
No, alkenal is gonna, so it has to be either arenal, which is this. It has to be arenal
Mhm.
or alkenal. It has to.
Oh, okay, okay.
Yeah,
I see
it
what
has.
you're
That's its one. It's the one caveat, and that's not a bad caveat to have. But it has to be, and same with the Suzuki as well. Okay, it has to be one of these types of systems. Just because the reactivity of something like this towards copper is just so slow. It's super slow. So it has to literally be this bond coming off because of the sp2 and because of the sp2 here. Okay.
Gotcha.
And copper would just leave with the propane.
Yeah, it becomes a copper lithium salt on the other end over here.
Oh.
So it's like, let's see, I believe this reaction actually kicks out the iodine here and kicks it out. And so you get out, I think on this one, you're gonna get out like lithium bromide, or not this one, lithium iodide or so. I think that's the byproduct that comes out, plus the copper regenerates. These are actual kind of cool reactions in that the catalyst does regenerate and you can reuse them.
Cool.
So it's kind of cool.
How come it only couples on one side?
Yeah, that's just what it does, because remember, this is iodine, right? So that's the same. So you have to have, there's a symmetry to these. So it's only one of them that's coming off on copper, okay? Yeah, kind of crazy carbon-carbon bond formation. Okay, the last one for today, before we get into some protecting groups, which is always kind of fun, is the Suzuki. The Suzuki coupling is, again, has to be arenal or alkenal, but these are nice couplings. So there's a couple. These are done through boron. If you look at boron, a couple different ones. This boron compound is one, and just because that's hard to draw that constantly, we abbreviate this one with two, that's that. Okay, it makes it a little bit easier than drawing that every single time. Drawing this bicyclo, right? It's gonna be a 3,3,1 bicycloborane complex. The other one that we see is the catechol-borane, which is kind of a nice one to work with. This is catechol here. We'll get into that when we get into aromatic chemistry, but it's that one. And so this one is abbreviated with the D, O, O, and then just that line. Okay. So again, it's just a way in the complex that you don't have to draw the entire thing. All right. So those are the boron complexes that we're going to use. Now, what's ultimately going on here? Well, what's ultimately going on is I'm going to take one of these and put an R group on the borane. All right. So the boron itself is I'm going to make a borane complex from one of these. Doesn't matter which one. This is catechol borane. This is 9-BBN. It doesn't matter which one of these you use. They both work nicely. But here's the cool part of this reaction. Again, when Professor Suzuki and his group worked on this, they took this phosphorus with all these phenyl groups on it. And so so you don't have to draw this all the time. This phenyl group is equal to that, okay? It's just a way of saying a benzene ring. It's a way of substituting that in. You'll also see that sometimes abbreviated just pH, phenyl, like that, which is why when we see the Suzuki coupling, it's typically gonna be pH 4 phosphorus, like that. 4,3. So, this massive molecule goes through a series of loss of the phosphorus triphenyls. Okay, so minus a P. All right, so your palladium then just spits one off. And I'll just do it this way. I'm just going to abbreviate it this way. P 5,3, so we don't have to keep drawing all those. Okay. And then it loses another one. To form this palladium here. And when it gets to here, okay, when it gets this far along, then what happens is the ligands attach down on this thing, and so at the same time, I'm going to take whatever my complex here is, and I'm going to hit it with sodium hydroxide. So what I take, and let's just say, I'm just going to put an R group on this, and it doesn't matter at this point what it is, and it doesn't matter which of these I use. But what happens is when I hit this with my sodium hydroxide then, because again it's electron rich, my sodium hydroxide then goes over and attacks the boron. Okay, remember boron is a Lewis acid. Boron is a Lewis acid. If you go back and draw a good Lewis dot structure for boron trifluoride, you'll remember that boron prefers to have that structure. Boron prefers to have 6 electrons, right? That's a good boron structure. But remember, the cool thing about boron, the reason why boron is such a powerful, especially in organic synthesis, is boron has 1 electron in the 2p orbital. So when it hybridizes to do this, it takes the 2s and the 2p orbital, and it mixes those, hybridizes those to an sp3, just like carbon, nitrogen, and oxygen do. So when it forms the hybrid orbital, the s, this is the 2s, and this is the 2p. So it hybridizes these to an sp3, but notice when boron, and again, it has 2 down and 1s as well. So it has 1, 2, 3, so it puts its electrons in here, okay? And so when hydrogen, or fluorine in this case, comes in, fluorine says, like, I'll share, and I'll make 3 bonds. That makes sense? Here's why boron is a Lewis acid. A Lewis acid is an electron pair acceptor, right? Lewis base is an electron pair donor. So here's an electron pair donor. I know that's a base. Here's an electron pair acceptor. Where does boron put that electron pair? Oh, it puts it in this open sp3 orbital. Okay? So that's how this behaves as a base acid reaction. So in this reaction then, I end up with this R, boron, OH, okay, causing boron to be negative. Isn't that kind of cool? Pretty trick, right? So that's why these reactions have this coupling around this is going to be the reacting, you can see what's going on right here. This boron here has an electronegativity of 2.5. This carbon has a 3.0, meaning these electrons now are going to be nucleophilic. Okay, nothing has changed from what we talked about. Meanwhile, up here with the palladium, this is ready to go. Palladium now reacts with whatever your Rx is, and again, it's going to be something that looks like this. And so then it puts the R across the palladium, and you can kind of see the theme here on these reactions are all very similar. And it puts the R coming out X. Okay? And what happens now is, as you can see, this, when this is added, it kicks off the X. Is that cool? Yes?
Does boron have an electronegativity of 2.0 or 2.5?
2.5, sorry. I just did those backwards, didn't I? 2.5, thank you. 2.0. Good, keep me honest. Okay, so in this case, then you're ready to go for the actual reductive coupling. You can see that whatever group was on the borane, and by the way, the borane R does not have to be alkenyl or aryl. It can be just like the copper one. It doesn't have to, but the Rx does have to be aryl or alkenyl. So now we're ready to roll. We've brought the palladium complex in. Okay. And you can see that again, once again, you get this cross-coupling reductive, and you get the R out. Kind of cool? And this is called Suzuki. It's the Suzuki reaction. And it's a pretty popular reaction. Okay. So the theme throughout this section of chapter 15 really is the complex of these big organometallic metals and organic compounds coming together and coupling, doing these reductive coupling reactions that form ultimately the carbon-carbon bond. Okay, so you could do something like, if I had something like this, and I wanted to couple this carbon to something. So let's say I wanted to go from that to this. Okay. How would I do that? Well, I could do that. I could ultimately do that through a Suzuki coupling if I wanted to. I could also do that through the copper reaction. Either one will work on that. So if I were going to do the palladium phosphorus 4. Well, I think I'm going to do peel. Let's do this way. Phosphorus, palladium, phosphorus 4. Okay. Rx. Well, in this case, let's just go ahead. Well, that is my Rx, and then hit it with 1, 2, 3, 4. So I hit it with boron. In this case, let's do something different. And that's basically how we couple these reactions. I do have to have the hydroxide in there, so these are typically done in sodium hydroxide or some form of a very strong base to get that, again, to get this reaction here. And that's it. Okay, Suzuki coupling reaction, again, nice coupling of aromatic or arenal reaction. Okay, any questions on those? pretty cool reaction. Copper and palladium. There's a couple other ones your book mentions. You can use ruthenium in this. I think these are the main ones. The copper lithium is really important. Suzuki is really hot right now in organic synthesis, so we should know the Suzuki coupling. And those are the two real. And then I personally like the alkyne reaction just because we can keep that handle on there and really work. And I don't have to have the limitation of it being arenal or alkynyl. Yes?
So why is the Suzuki one so popular?
It just is. It's just, again, carbon-carbon bond formation is really powerful, and it's a really high yielding reaction.
Why that specific
Yeah.
form of carbon?
Probably its yield.
Oh,
Really high yields on this. Copper is not as friendly as palladium. So with the copper coupling, copper is also a little bit more caustic on the environment. So there's reasons why the Suzuki is used, but it is one of the, you see it all through synthesis right now. It's when it first came out several decades ago, it was like, this is the hottest thing, the hottest new thing. Okay, I'm gonna end the chapter this way. We are going to be continuing to build on our synthesis. And one of the things that we want to keep in the back of our minds the entire time is, what is the susceptibility of the functional groups I'm working with? So there are times in synthesis where you have to protect the functional group. If I'm going to protect something like, if I have an alcohol on my molecule, and I don't want to destroy the alcohol. I don't want the alcohol to oxidize, or I don't want the alcohol to form an ether. I need to protect it. So there's a couple different ways. I actually have, from graduate school, it's very interesting. This is a massively important and massively large field of organic chemistry. I have a book that's probably about a 500-page book. It's called Greens Protecting Groups in Organic Chemistry. So with that, you might be doing a synthesis that has an amine on it, an alcohol on it, and a ketone on it, or an alkene on it, or something. And you want to do a reaction, but you're looking at that, and you think, I can't do a reduction of a ketone and an alkene together because it's going to reduce both. How do I work with that? So just there's three main types of compounds that we're going to protect with. One of the ones that we use oftentimes with alcohols is some form of silane. Okay, these are real. There's bunches of these. So if I take something like silane, and let's say my compound has an alcohol on it, and I want to protect it. Let's just make a random secondary alcohol. What I can do with this is I can take the silane group and I can remove the proton, and I can what's called protect. Okay, I can protect this thing. So an oxygen silicone bond is not susceptible to oxidation. It's not susceptible to SN2 to form ethers. So if I want to protect an alcohol, and again, there are literally hundreds of forms of the silicone type of, and they have funny names like MOM and MOT and MORE, and they're just, and you'll see those all through organic synthesis. So I'll take a functional group that I've worked hard to establish, and if I've got something else in this molecule that I'm going to beat up, I protect this, because then I know if I add this to some type of strong acid, like hydrofluoric acid, then I can just take that right off and reestablish my alcohol. Okay, so this is called protecting group or protecting group chemistry. Okay, these are a couple of the ways that I can do that. And I'm not going to go super deep into this, but I do want you to at least see that this is an area of organic synthesis that's actually very important to use, especially if you're working on a molecule that has multiple functionality to it. Right? And most of the time you're working with organic synthesis, you're working with multiple functional groups. The other one that's really important, and we'll come into this when we get to ketone chemistry and actually carbohydrate chemistry. If I hit this ketone with ethylene glycol, okay, and para-toluene sulfonic acid, it forms a really interesting compound called a ketone. And it's an actual functional group. It's a ketone. So what it does, which you can see happening here, these attack, that's what's going on. Okay. And so it protects this. But what's really nice about the ketone, or in this case, they also call them acetals, but in this is specifically a ketone. Any kind of acid, if you're really careful with it, you can beat that thing up with an oxidizer, with a reducer, you can hit it with a strong base, it won't budge, that carbon. That carbon is locked. The minute I breathe acid on this thing, it goes right back to the ketone. Okay, not cool? So it's a nice way in organic chemistry to work with compounds. For example, if I had, and I'll show you where this might be important. Let's say I wanted to work with something that had polyfunctional group, polyfunctionality on it. Okay? So let's say I have a molecule that looks like this. And I want to do some work over here, but I don't want to destroy this. Okay? How would I accomplish that? How would I work with that? Well, again, this is where protecting it, hitting this with the ethylene glycol, para-toluene sulfonic acid, it's just a form of an acid to protonate the ethylene glycol, that fuses to the ketone. That, all right? Doesn't put it on the alkene. Alkene is fine. So now I've got my protected ketone, and I can do work on this, right? I could hit that with osmium tetroxide, making a diol. That would be kind of cool. I could hit that with, I'm trying to think what else, MCPBA, and make the epoxide. So let's do that. So if I hit this with MCPBA, I could put the epoxide on. Okay. And then if I hit this with acid, notice I'm going to, acid's also going to open this thing up, and you probably learned that you're going to open this up favoring the non-hindered. So that's going to go there. So that's going to give you so if I did it right, 1, 2, 3, it's going to be these right here. Okay. And so again, this is a whole strategy that we'll work with, because ultimately, like I said, ultimately what happens with these multiple functionalities is there has to be a way to do the reaction that I want to do without destroying the molecule. So this is just a small, tiny glimpse into a massively important and big field of strategies in organic synthesis. Okay? All right, so let's go back and let's do a little practice, and this is kind of a glimpse into what Wednesday's going. Let's use some of the reactions that we've seen over the past 3 chapters. So let's say I wanted to start with, I'll give you a couple minutes just to think this one through. starting with acetylene, propose the synthesis of that. See what you get. See if we can use some of those reactions that we know. And I'll tell you, I just want you to look at that a little bit, and then I'm gonna work you through in the last 15 minutes of class, or I'll give you about 5 minutes just to kind of think it through. And then I'm gonna work you through how to approach synthesis problems, retrosynthesis, and I'll explain what I mean by that. I'm gonna go grab forgot my cup of tea.
Yeah, and we need to sodium, ion at the beginning. Stuff, and then that breaks the so then we can do the maybe second hydrogen
I was snowboarding.
Were you snowboarding?
Yeah. I saw the results though.
Yeah. Did you get to watch like the last minute?
I saw some of that.
You saw the highlights.
Yeah. It was.
Yeah, for you guys. I mean, it was a sweet moment for Nogales and me, but boy, that's hard to lose that way. To lose with a, to lose with a turnover like that. And Garoppolo had so many weapons to get down the field.
Oh, 100%. Yeah.
All they needed was a field goal.
Yeah.
Right? Just don't turn the ball over.
Yeah, exactly.
It's like the worst thing he could have done. Granted, he probably should have just gone down or thrown it out of bounds, but it would have been fourth and, well, if they tackled him, it would have been 4th and 20 something, but as it was, it would have been 4th and 15, but it doesn't matter. At least you live to the next play.
Yeah, exactly.
You know?
You get one more shot.
You get one more shot at it.
Yeah.
So that was kind
Especially
of
with Debo, like
yep,
all of those guys.
exactly. So I was like, oh man, yes, but you're like, ah.
I was hoping that Trey Lance would be our starter by now.
Oh.
He'll need another season or.
You think so?
Yeah. And then maybe we'll see.
Okay.
Yeah.
You don't like Garoppolo?
He's a solid quarterback. He's taken us to the Super Bowl already, and then he's won besides I think Tom Brady and one other person. He's won like the most playoffs as a quarterback in like a while. So like he puts up results, but he said I don't think he's like Tom Brady. Or
Yeah. Well, and that's the same with us with golf. I was a huge golf fan. Actually have a split jersey.
Really?
From Cal and from Rams,
That's
and he
awesome.
and he signed it for me.
That's awesome.
It was
Wow.
really cool because it was like he was 16 at both at Cal and at the Rams,
Uh-huh.
and it has golf. So I had to buy 2 jerseys, and this company sewed them together. And then he signed it, so it's on the back. It's golf number 16. It was really, he thought it was really cool.
That is really
Because
cool.
I didn't even think about that. So anyway, but I really liked him as a quarterback. But
Yeah.
he was just he
Yeah.
could be 45 points or he could be 3.
Exactly.
And
Yeah.
you can't have that.
Exactly. You need some stability or some
Yes.
consistency.
Yes. So it's just like, come on, dude. So anyway, and he's getting beat up in Detroit.
Yeah, that is a bummer. It's rough.
Okay, hopefully you've had kind of a chance to at least think it through. Here's the way I would assess this. In your mind, be thinking, okay, in my toolbox, how many reactions do I know that form carboxylic acids? How many can you think of? From the last 3 chapters. I can think of 2. One is,
Oxidation.
yes, oxidation of a
Alcohol.
primary alcohol. Okay. What else forms a carboxylic acid? Okay, well that's oxidation. Yeah. Yeah. Okay. Aldehydes and aldehydes and primary alcohols oxidize carboxylic. I consider that the same one. Okay. What other reactions? A very different reaction that forms carboxylic acid.
Ozonolysis under oxidation.
Boom. Ozonolysis under oxidative conditions. So you have 2 different ways you could go with this. Okay? So one way that you could go about this is I could see this coming from, here's the thing. In synthesis, we want to be looking at the site of reactivity. Carboxylic acids can come from one of 2 things. I could come from a primary alcohol, okay, or as Clayton said, I can come from an aldehyde, either way, okay? I consider those the same.
Yeah.
Or I could have come from an alkene. Right? So this route takes my reactive center and says, oh, well, I know how to make a non-Markovnikov alcohol from an alkene, and I know how to make an alkene from an alkyne, and I know how to put carbon groups on an alkene. Right? Or, likewise, this one I had to think through in my buildup. I'm going to lose 1 carbon in ozonolysis, right? So if I want 4, 1, 2, 3, 4, I had to have 5. All right, so that then would have come from this. 1, 2, 3, 4, 5. Okay? Which, again, I know that could have come from that. So you have to kind of assess the situation. Which of these, I'll do both, we'll go both directions with this. Which one of these requires fewer steps? And that doesn't always mean it's better, but what's the whole Occam's razor? The shortest way from point A to point B is probably the best way, right? If I don't have to go through D and E to get there, why do it, right? So let's go build this reaction. I'll build it over here. So that's the retrosynthesis. Now let's do the forward. Let's actually put these reactions together. So I'll do the top one first. What are the steps along the way of building up this alkyne? Okay, so let's start with acetylene. I'm going to hit it with sodium amide in ammonia, and then I'm going to hit it with basically ethyl bromide. Okay. That's going to build up That's gonna give me my 4 carbons. At this stage of the game, I need to reduce it. So I'm gonna pick Linlar and hydrogen to reduce it down to the terminal alkene. Okay. Now I need to do a non-Markovnikov hydration, which I don't know how you guys did them. I don't know if you did B2H6 and diglime. Is that what you guys did? Or did you do BH3 THF? I don't know which way you guys did that, but it's a boron anti-Markovnikov hydration, however you did that. Typically, this then has a first step of that and then a workup of hydroxide. Okay, so that's going to give you the primary alcohol. And under strong oxidation, KMNO4 or chromic acid, either way, it's going to oxidize to, I just flipped it around, it's going to oxidize to the carboxylic acid. Okay? How many steps is that? That is 1, 2, 3, 4. Do I not like any of the steps? No, those are all really good reactions. This is a really high yielding step. Linlar is almost quantitative, probably 98%, really nice reaction right there, mild reaction. It was actually a really nice reaction, probably in the 80s, maybe low 70s or mid 70s. This is almost quantitative oxidation, as long as you don't burn it up too hot, it's good. So all those are great reactions. There's no bad chemistry, there's no weird chemistry that goes on. So let's do the other route and see, let's assess it as well. So sodium amide, ammonia. I'm gonna add 1 more carbon to it. So instead of ethyl bromide, I'm gonna use propyl bromide. Propyl bromide then comes in and puts that there. And just for the record, I didn't show you this, but I will show you now. If you hit this with ozone in oxidative conditions, it'll actually go straight to carboxylic acid. So ozone is actually a molecular scissor both on alkenes and alkynes. It'll cut it right there. I didn't show you that, so how would I have done that without showing you that? Well, I would just gone ahead and hit it with Linlar. This one I do know. Okay, that's going to go to that. And then if I hit this with ozone under oxidative conditions, it oxidizes the carboxylic acid. Okay. So again, I have 1 less step doing it this way. I did lose a carbon in the process. That's not bad. Those aren't very expensive. You know, the difference between propyl bromide and ethyl bromide is pennies, so that doesn't matter that I had to cut that off. Any bad reactions? Ozone is a nice reaction. Linlar we already used, so you know these are identical. This is probably the lowest yield reaction of all 7 of these reactions. Both would be acceptable. I'd probably prefer the bottom one. Definitely prefer doing 2 steps. Boom, boom. That's a really nice reaction. Cool.
So in the first one, you only added 1 carbon.
2 carbons.
You had 2 carbons.
Ethyl bromide. Yeah. So I had 2. I added 2 because I have to have 4. Second, the bottom one, yes, I had to add an extra carbon because I cut it off.
Okay.
Cool. This is what we will do on Wednesday. We will practice, and we will hopefully these that will be on the exam, you'll be good to go. Okay, then we'll just keep on building, keep on trucking. All right.